Swayamprabha. Digital India. Educated India.
Greetings and welcome again to this course. Last two classes we had seen in detail about different types of interpolation to obtain variable value on phase. Why do you want to do that? Because in convection term you have the variable value appearing and they are to be evaluated on control surfaces. Accuracy of the scheme depends on what type of approximation you are using, and we had seen 5 approximation procedure: central differencing type approximation, pure upwinding, hybrid scheme, power law scheme and quick scheme. We had seen all these different approximation in detail, mathematical formulation for different situation, and how to put along with diffusion equation discretization a generic formula, finite volume difference formula, and how these coefficients are related to each other. So, node of interest coefficient is related to neighboring nodes, and in the case of pure upwinding we had a term called alpha which decides the direction of the flow. According to the direction of the flow the switching happens. Similarly, in the case of quick scheme we had a factor by name beta which again depending on the direction of the flow it takes appropriate weightage or the correct direction and switches. In today's class and followed by next class we will see with an example how each of the scheme behaves for different mesh size for the same problem, get a feel for performance of each of the schemes. Just to recapitulate, here is an illustration for quick scheme, and we already learned in quick scheme you have a quadratic fit through 3 points. 2 points are on either side of the node of interest and one additional point in the direction of the flow. We have seen so far mainly 3 approximation: central differencing type, pure upwinding and quick scheme. In this particular slide we will see all of them together, get an idea of how these coefficients are different for each scheme. For both CD type as well as pure upwinding scheme, finite volume discretized equation is written as shown: AP pi p equal to AW phi W plus AE phi E. As we said many times before, P is a node of interest and it runs from, for the case of 1D, left to right, and AW and AE are neighboring nodes coefficients. So, node of interest coefficient AP is related to neighboring node coefficient. In the case of CD, expression for coefficients for AE, AW, AP are shown. Similarly, for pure upwinding, coefficients for AW, AE as well as AP are shown here. You can understand now very well the difference in the term if it is central type and if it is pure upwinding. In the case of pure upwinding we introduce a term called max of FCW and 0. So, it takes between the two whichever is the maximum, which is actually introduced for the purpose of direction of the flow. So, if the direction of the flow is from left to right, then it is positive FCW will be used in that expression. Similarly, if the direction is negative, then FCW will be negative, 0 is the maximum, then accordingly 0, that contribution from that node will not be considered. This way of writing is helpful when you are writing the code. It automatically switched between one side to other side based on this control. Next we will see quick. In the case of quick, then we get expression AP pi p equal to AW phi W plus AE phi E plus AEE phi EE plus AWW phi WW. You can immediately observe the quick scheme has two additional term. Once again, this is a generic expression, generic in the sense it accounts for any type of flow direction. So, when you compare CD or pure upwinding, quick scheme has two additional information. From quick scheme has information from one additional node, and that one additional node depends on the direction, and that is put in the generic expression as shown here. And AP, as we did in other two scheme, once again related to neighboring nodes. So, AE AW and AE E as well as AWW, an additional term. Correspondingly, you can write down coefficients. So, AW, AWW, AE and AEE. We have introduced new coefficient beta, again that is decided based on the direction of the flow. If beta is equal to 1, then the flow is from left to right, it is positive. If the beta is less than 0 or equal to 0, if the flow is from right to left, then accordingly corresponding weightage is taken to determine the coefficient values. So, for example, if beta is equal to 1, the term in AW, this particular term is 0, there is no contribution from west node, flux contribution from the west phase, then that is used here. Similarly, you can try to understand based on different values of beta coefficient expression, and it is a generic expression. So, this helps in writing one code with different switching control option. Now, you can also get a curious question whether you can have code written employing, for example, all the three schemes, that is CD, pure upwinding and quick. The answer is yes, because coefficients terms have same structure. As you can observe here, for example, AW has a similar structure, only additional terms are introduced. So, you can calculate for CD and switch to pure upwind or switch to quick depending on the scheme that you are deciding. That automatically is also decided based on the direction of the flow. Now, we will take an example problem and try to get idea about performance of these schemes. The problem statement is given here. The figure shown is for one dimensional, the flow is from left to right, x is from 0 to L is the length of the problem. Variable value at the left side is given as a boundary condition phi at 1. Similarly, the variable value at the right side phi equal to 0 is given on the right side. The question is solve the problem by a different approximation scheme, CD, pure upwinding and quick. Now, to get an idea of how these schemes behave for different flow condition, we take two different flow condition, u is equal to 0.1 meters per second, another condition u is equal to 2.5 meters per second. Then to get an idea of for the same speed, if you discretize with the 5 mesh points, if you discretize with the 20 mesh points, what is the difference between 5 mesh points and 20 mesh points? The delta x is decided, the delta x term goes into the expression of coefficient calculations. So, to understand how this mesh spacing also influences accuracy, we have another case, solve the problem with the two different mesh size one for 5 equally spaced mesh points, another 20 equally spaced mesh points. Now, in the further illustration, we will not do all the combination, we will only look at few combinations and get an idea of performance. In the last slide, we explained the problem. Now, let us get some more explanation. 1D domain with the boundary condition phi at 0 equal to 1, phi at L equal to 0 when x is equal to L is now discretized with 5 equally spaced cell, and for the problem define rho is taken to be 1.0 kg per meter cube and gamma taken to be 0.1 kg meter per second. Let us take two cases, and this is a domain. We discretize the domain with 5 equal nodal points 1, 2, 3, 4, 5, and they are equally spaced. So, you see delta x as the distance between node 1 and 2, same way the distance between node 2 and 3 and so on. Because it is equally spaced, node 1 which is a node near to the left boundary, similarly node 5 which is a node near to the right boundary, both are at a distance of delta x by 2 with respect to the respective boundary, and boundary conditions is already shown here both on left side as well as on the right side. And for this problem, analytical solution is already given, and that is what is displayed here. Now, we take one of the case, that is u equal to 0.1 meters per second and 5 mesh points. We calculate convective flux as well as diffusive flux. Convective flux equal to rho into u. Rho is already defined as 1 kg per meter cube and u is 0.1 meters per second. So, rho u you will get 0.1. Similarly, for diffusive flux, it is defined as gamma by delta x. Gamma is 0.1, delta x is 0.2, and that is equal to 0.5. We want to evaluate convective flux as well as diffusive flux to get an idea of role of convective flux and diffusive flux. Now, this relation or weightage between convective flux and diffusive flux will inform or tell us about performance by different discretization scheme. We first do central difference approximation. We have already seen expression for coefficients. Now, we substitute these values, that is FC, FD value in the expression for each nodal location, and we get values as shown in this table. You can observe immediately node 1 left side is a boundary condition, hence AW is 0. Similarly, for node 5 the right side is a boundary condition and AE is 0. These are cross checking, and the boundary condition on the left side as well as on the right side appears as a source term, and that is also shown here. For all internal nodes for this particular problem there is no source, hence they go to 0, right. And we also mention point of interest node P runs from left to right. In this case it runs from 1 to 5. We also mention point of interest node coefficient AP is related to neighboring nodes coefficient, and that is what is written here. AP is related to AE plus AW minus SP, and you can cross check here. Take any one example, for example node 2 0.55 for AW and 0.45 for AE, and there are no source term, hence AP is just 1 and it is shown here. Now, you can write this in the form of a matrix, and that is shown here. So, if you write AP phi P is equal to AE phi E plus AW phi W, and that is what you will get, the matrix. Okay. These coefficients are already calculated, Now if you look at this, this is a coefficient matrix multiplying unknown variable column vector, that is on the left side, on the right side known value column vector. So this P runs from left to right, that is from 1 to 5, and that is what is given here as unknown column vector. So this matrix, if you look at, there is one main diagonal and elements along the main diagonal 1.55, 1.0, 1.0, 1.0, 1.45, and there is an immediate super diagonal and immediate subdiagonal. All other elements in this matrix are 0, both above as well as below. Such a matrix which has only 3, one main diagonal just above and just below, is what is known as a tridiagonal matrix, and there is a separate procedure available, what is known as a tridiagonal matrix algorithm. We will be looking at that detail in subsequent class. So once you invert this matrix by that procedure TDMA, tridiagonal matrix algorithm procedure, then you get all these values at nodes 1 to 5. We also have a expression analytical solution. So we compare results obtained by analytical solution against results obtained by central type approximation for this particular case, and that is what is shown in this graph. Because the problem is very simple, the velocity condition is only 0.1 meters per second and 5 nodes we have only considered. The solution happens to be almost same as exact solution. So in this case there is no serious remark in terms of performance. It is only that for this condition CD exactly matches or very closely matches with the exact solution. Let us take performance, let us look at the performance by Uppin scheme. We are not going to the details of how each coefficients are calculated, because for this problem with this value of 0.1 meters per second and 5 nodes and density value and diffusion coefficient, it is very easy to calculate those coefficient values. You can get again from the generic expression, get the matrix and solve, then you get solution by this Uppin scheme, pure Uppin scheme. You observe here pure appending scheme, it matches with the exact solution for some points and then there is a deviation. So this is pure appending, results obtained by pure appending, and this is a solution obtained by exact solution. There is a discrepancy here, whereas in the previous case for the same arrangement the difference is only in the scheme, that is central differencing scheme, and here it is pure appending, the solution almost matches. Let us look at the performance by third scheme, that is quick scheme, and we learned the quick scheme has 3 nodes, one node on either side and one extra node in the direction of the flow. In this particular example problem, the direction of the flow is only one side, that is from left to right always, and so the performance almost matches with the exact solution. Okay. We will look into this quick formulation in detail in the next class. This idea here is to show performance by quick scheme also in addition to performance by pure upwind as well as CD. Now the second case is a higher velocity, u is equal to 2.5 meters per second for the same problem, that is same domain, number of mesh points are same as 5. U is increased from the previous case 0.1 meters per second, now it is 2.5 meters per second, which means it is convection dominated. Hence you get flux values calculated to be 2.5 and diffusion value calculated to be 0.5. Now you can get an idea of ratio of convection flux to the diffusion flux. It is a convection dominated problem, and we know the transportive property is ensured better in pure upwinding when compared to central differencing. So we again get details of all coefficients by one scheme. In this case it is central approximation with, for this condition, u is equal to 2.5 meters per second, maintain number of mesh points to be 5, and we get coefficient as shown here. Okay. These are individually calculated, and what is shown here is only the final value. Now if you look at the performance, as I have been telling before, velocity has increased from 0.1 meters per second to 2.5 meters per second. It is a convection dominated problem now, hence a CD scheme will not be able to capture the direction and the performance is not up to the mark. Once again, what is plotted here is exact solution, and performance by central scheme, as you can see, there is a wiggle, it is ups and down, and it is limited by the boundary condition on one side as well as on the other side. Okay. For the same problem, that is velocity condition is 2.5 meters per second, but the number of mesh points is now increased from 5 to 20. In that case, the diffusion flux where delta x appear in the denominator is increased to 2.0. So if you compare convection flux and diffusion flux, the order is almost the same, that is 2.5 and 2.0. This is convection flux and diffusion flux meant for that particular control volume. Okay. So for the same problem, velocity condition is the same, 2.5 meters per second. All that we have done, increase the number of mesh points from 5 to 20, same scheme, that is central approximation. Once again you calculate all the coefficients. So you can see node 1 which is near the left boundary, and node 5 which is near the right boundary, and all others are internal nodes between 2 to 19, and we get coefficients calculated. As we have observed before, internal nodes, there is no source generation, hence they are all 0. The boundary condition appears through source term for near nodes, that is what you see here, node 1 and node 5 they have value. Once again you can observe AP is related to neighboring coefficient, you can again cross check these values. Okay. Now you see the performance, the same scheme, central difference scheme, for the same flow condition 2.5 meters per second, when it was with 5 mesh points, it exhibited wiggles in solution. The wiggles have gone by increasing the number of mesh points from 5 to 20, and we get solution very close to the exact solution without any oscillation, ups and downs. Okay. So this is the way you can improve the solution accuracy if the order of accuracy is constrained. So in this case you decide to have a central difference scheme because it has a second order accurate, but it exhibited a wiggle or oscillating type of a solution. Now you can increase the mesh size and get away with the oscillation and get a improved solution. For the same 2.5 meter per second with the 20 mesh points, we like to see the performance by pure upwinding. We already know the pure upwinding has a property in the direction of the flow, hence in this case the performance is not very surprising. The performance by the pure upwinding is almost same as the exact solution. Now with this we looked at performance by two different scheme, mainly central difference scheme and pure upwinding for one particular problem, and two different flow condition and two different mesh condition. So if you change the mesh from 5 to 20 for the same flow condition, quick gives better performance or improved solution without any wiggles as well as oscillation. Pure upwinding, it performs better if you increase the mesh size, the diffusion part is reduced. So in the next class we will take the same example problem, we will try to understand performance by quick scheme, and then we will put performance by all the scheme together in one plot and get idea of performance by all the scheme. Thank you.